In all cases, we have the distributed logical router functionality, where it looks like all the switches would be part of the same router, which means that all the switches must have the same IP address, and all the switches must listen to the same MAC address associated with this IP address, so that every switch receives a packet sent to the router, to the first hop gateway, as soon as possible, then does layer 3 forwarding, and forwards that over another virtual segment to the other side. Let's do an example here. Let's say the orange VM wants to talk to the blue VM. The orange VM knows that the blue VM is in a different subnet, so it will send the packet to the first hop gateway. In this case, the MAC address of the first hop gateway is present here, so the logical distributed router will get this packet, and it will do layer 3 forwarding, and now it will forward the packet in a blue segment to the blue VM. The blue VM will reply to the packet, and it knows that the orange VM is in another segment. So the blue VM will send the packet to the default gateway on the blue segment, which also happens to be present here. And so the first hypervisor switch catches the packet, does layer 3 forwarding, and then forwards the packet in red segment to the red VM. So you see, the switch between subnets always happens on the ingress hypervisor. And you also see that every hypervisor obviously must know about the routing, so it must have the full routing table for the logical domain. Also, every hypervisor has to participate in every single subnet. So even though this hypervisor here only has blue VM connected, it has to participate in the blue and in the red subnet. Likewise, the top hypervisor has to participate in the red subnet, obviously, but also in the blue subnet, because when it sends the traffic to the blue VM, it has to be part of the blue subnet. Which means that the moment you turn on distributed logical routers, every hypervisor has to participate in every logical subnet in the whole routing domain. Even more, when the top hypervisor tries to send the traffic to the blue VM, it obviously needs to know its MAC address. So it has to have the full ARP table for every segment in this logical routing domain. So you see, from the scalability perspective, distributed routing is way more complex than distributing layer 2 switching. First, every switch must be in all layer 2 segments. Second, every switch must have forwarding entries for all the VMs in the whole routing domain, not just in the local segments. It must have ARP entries also for the whole routing domain. The traffic flow, as I explained, the traffic is sent to the VM MAC address, which is always resident on the local hypervisor, and then the traffic is intercepted by the local hypervisor and sent to the other VM. On the other hand, if VM A here would send traffic to the MAC address of VM B, then this MAC address is not the MAC address of the hypervisor, so it's sent straight to VM B. So if the traffic is sent to a third MAC address, not the MAC address associated with the logical router is not involved. Pure layer 2 forwarding is performed. Also, if A sends a broadcast, or if it sends a packet to X and we don't know where X is, this will be flooded to every hypervisor that participates in the red segment. Only if the VM sends the traffic to the logical router's MAC address, then we do a layer 3 forwarding. And yet again, remember, all the processing, including header rewrite, TTL decrement, and layer 2 forwarding in the outgoing segment is done on the ingress hypervisor. Now, with NSX for multiple hypervisors, the logical router is a purely virtual construct. It has no control plane protocols. Now it supports static routing, but still no dynamic routing protocols, apart from ARP, which is handled locally in the hypervisors. Layer 3 forwarding programmed from the controller and implemented in Open vSwitch. And the Layer 3 daemon that is resident in every hypervisor populates both ARP cache and the OVS forwarding table. If you want to, you can connect a gateway node to a distributed logical router, and then the gateway node would perform the functionality we have discussed before, whereas the kernel modules in the individual hypervisors would perform the east-west traffic forwarding. Now, gateway node can still do NAT, but the hypervisors modules can't. So if you do forwarding between VMs, you cannot do NAT. If you want to do forwarding from the VM to the outside network through the gateway or vice versa, then it's possible to do NAT. In the vSphere version, the Layer 3 forwarding is implemented in the kernel module, as I said, but we need a control VM. The control VM is yet again vShield Edge with the distributed router functionality. So it's purely a control VM. It does not touch the forwarded packets. The only thing it does is it runs routing protocols, so it can connect reachability information from the outside world. So it collects all the routing information, it pushes that to the controller installs that information in Layer 3 modules in individual hypervisors, and then the Layer 3 modules do the distributed Layer 3 forwarding. ARP processing, slightly different from the NSX for multiple hypervisors case. Here, the controller is the authoritative source of ARP information, and the individual hypervisors use the VDS security module that I mentioned previously to report what MAC and IP addresses they're seeing and report that to the controller. And the controller so can build the full ARP table for the whole virtual network and then either download that information to the forwarding modules, or if the forwarding module is missing an ARP entry, it would query the NSX controller on the cache miss. In the NSX for multiple hypervisors case, I told you that you can sort of merge the distributed router with the gateway node. Here, you need two VMs. But first, let's cover the case where you don't want to do any NAT or any other services. So you just want to run overlays Layer 3 to the outside network. You can still do that with the distributed router control VM, which would run, for example, in my case, BGP with the outside world, and then the kernel module on the host on which the active control VM sits, so the same rules as for Layer 2 gateway, would perform Layer 3 forwarding between VXLANs and the outside world. If you need services like NAT, then you have to connect the distributed router with the services router. So how do you do that? Well, you create an extra VXLAN segment and you connect the two virtually over this extra VXLAN segment so that they can run routing protocols. And then the forwarding bypasses the distributed router and goes straight from the edge services routers to the VM using the Layer 3 forwarding modules in the hypervisors. The edge services router becomes sort of default gateway. So the Layer 3 forwarding modules know that they have to send the IP packets to the services router, and then the services router can do whatever it needs to do, including NAT, load balancing, firewalling, and so on. Personally, I would recommend that you run OSPF within the cloud, so between distributed and services router, and BGP between the virtual and physical network. But that's just my recommendation. You can run any routing protocol you wish anywhere on this whole picture. Is there a roadmap or timeline for IPv6 support, particularly as it addresses distributed routing functionality?
So there is some IPv6 capabilities at various parts of the stack in there today. So you can do IPv6 static routing on the NSX Edge Services router today. Dynamic routing for IPv6 is something that's on our roadmap.
So the distributed router, at least in NSX for multi-hypervisor case, supports only IPv4 today, right?
That's right.
And with NSX Edge Services router, you can already do IPv6 today.
IPv6 static routing.
Next one, is there a hardware that would decap VXLAN and do a VRF lookup on the hardware at the core? In theory, you could do a bit of that with the Arista switch. In practice, look at the list of NSX partners that was published at VMworld and talk with them. What's the throughput for layer 3 gateway?
Throughput for the layer 3 gateway. Are we talking about vSphere or multi-hypervisor? Well, I could answer
Probably both.
No, I think the answer is going to be the same in both. You're close to 10 gigabits. If you got a Sandy Bridge server with an Intel 10 gig NIC or whatever 10 gig NIC, you're going to be able to get pretty close to line rate on that.
Some people don't believe us, so the next question is, what packet size is that?
So we've done a lot of testing on this. We've seen this in our customers. We'll be publishing a lot of details on those tests along with the GA release of that. I believe there is a slide coming up, Ivan, on performance, and there was some specific testing that we ran in that performance. So for example, we were doing a lot of testing with HTTP traffic and getting a certain HTTP web page, I think a 200 kilobyte web page, and we're just doing that over and over again. So about a third of that traffic was TCP, SYNs and ACKs, and session management. The other 2/3 of the traffic was TCP maximum segment size, which is about 1500 byte.
The next one, I wouldn't do this, but here's the question. Can layer 3 gateway support full BGP table?
The layer 3 gateway and NSX Edge Services router, we can do BGP, but we have a certain limit on the number of routes we can hold. I think it's in the 240,000-ish range. So I would not at all recommend trying to bring a full internet routing table into that.
I would never do that, and I really can't see a use case. But okay, there was the question, had to ask. Here's one about the support for more fully featured third-party routers like Vayata, and you can always use them as a VM with multiple NICs, and you configure and orchestrate them on your own. Can we do NAT between the internal subnets? We know it cannot be distributed, but if it goes through the gateway or through a services router, can we do NAT between the internal subnets?
Yes. So the NSX Edge Services router can do NAT between interfaces. So that's where you would do it. The traffic would go through two interfaces there. NAT would be performed. We would not be doing NAT on the distributed routing from hypervisor to hypervisor directly.
For routing, do different subnets have the same or different VXLAN ID? Because they are different layer 2 subnets, they have to have different VXLAN ID. So every layer 2 subnet has a different VXLAN ID if it's implemented in the overlay network. Here's a good summary of what I said. So in the NSX Edge distributed router, the question is, so the control VM is where the RIB lives, or routing information base, and the kernel module in the VDS is where the FIB lives. And that's a perfect summary. So we have RIB in the control VM, and we have FIBs all around in the hypervisor modules. Next one, why do you prefer BGP as the routing protocol between internal and external? For a very simple reason. Once you are part of the OSPF domain, there is no filtering. So any node can insert anything in the OSPF domain, and it will be flooded to all other members of the same OSPF domain. As the physical network administrator, I would still be cautious and wouldn't want the virtual appliances to participate in my core OSPF routing, because then, in theory, any misconfiguration of a virtual appliance can bring down the physical network, Whereas BGP would be safe for me because I can filter inbound updates and decide what to accept from the virtual appliance and what not to accept. Next one, if it supports ISIS, are there any downsides to using that in the virtual environment? Well, I would say that it depends on which language you prefer to speak. So wherever it runs OSPF, there's no reason why you wouldn't run ISIS or vice versa. It just depends on what you're more familiar with. But as I said, between physical and virtual world, I would stick with BGP. Can you constrain a group of ESX hosts to use a specific DR edge and have many DR edge instances? No, you can't. The DR edge instance is tied to a layer 2 or many layer 2 segments. And wherever those segments are, that's where the VMs will send the traffic to a DR edge. So if you want to sort of constrain the traffic flow, then you have to be careful about the VM placement. This ties to another question about the trombones that are introduced by virtual appliances. And so I really want to go back to this slide. A while ago, Brad persuaded me that all my ideas about trombones are wrong, and he was right. Because if you have a firewall here, for example, then the traffic from VMA going to VMB, for example, and has to pass through a firewall, yes, it will go over here and it looks awful, but remember that because we are using class fabric, everything is equidistant. So it doesn't matter that it looks like the whole thing is going across the fabric. It could easily be going from here to here and then back. And also, you wouldn't connect your physical firewalls in the fabric core usually. You would usually connect your physical firewalls somewhere here as well. So the traffic flow is no different in the physical and the virtual world. So yes, it looks ugly. It looks like there are traffic trombones and the firewalls between subnets are always a choke point. But with leaf and spine fabric, at least it's the best you can do, and it's no different from the physical world.
I don't know if this is entirely related to the question or not, but one thing I wanted to mention while we're on the topic is that on the NSX for vSphere and the NSX Edge Services Router, remember each tenant could be deploying their own NSX Edge Services Router with their own, multi-tenant virtual firewall and load balancer. And those are placed in a vSphere HA and DRS cluster. So you're getting a number of benefits from that. You're getting dynamic service placement. So the HA DRS cluster is going to move those edges around to the best host that's lightly loaded. You're always going to have perpetual N+1 redundancy. So if one of your edge hosts fails, your NSX edge is going to be restarted on another host. And remember, there's always two of them anyways that are syncing state with each other, and vSphere HA is keeping them up. So you've got perpetual N+1 redundancy. And then you also have the ability to leverage vSphere HA and DRS affinity rules. So if you had a really important application that you wanted to make sure had lots of bandwidth for its firewall and load balancer, you could create a rule that said, okay, this set of edges will be placed on these handful of edge hosts here. Meanwhile, all of the other edges from all of the other tenants can fight it out on all of those other hosts over there. So you do have that capability to kind of define where services are placed and then get the dynamic placement, ongoing optimizations as the cluster's running.
Yeah, I think the question was coming, at least as I understood it, more from the perspective, if I don't have an equidistant data center, can I use one instance of the edge router for nearby VMs and another instance of the edge router for other, let's say, distant VMs?
Okay. I think you answered that question perfectly already.
Yeah. With multi-hypervisor, if we have distributed router and a layer 3 gateway, does the gateway share the same router IP on each segment? Or does the distributed router need a static route via a different IP on the gateway? So in the multi-hypervisor case, the distributed forwarding functionality and the layer 3 gateway look like one IP router. So there is one IP address and one MAC address that all of them use. To find other virtual networking, data center, and cloud networking webinars, visit ipspace.net.